questions related to maxima and minima. Write down subheading as questions related to maxima and minima. Questions related to maxima and minima. Right. People will take as the very first question the question number 89. Take question number 89 as the first question today. Right. Take question number 89. You are given there something like this. Show that among all the rectangles of given perimeter, the square has the greatest area. The square has the greatest area. Right. So first you have to understand the question here. Show that among all the rectangles of given perimeter, the square has the greatest area. Now people, suppose we are given to draw a rectangle whose perimeter should always be 50 centimeters, like this. The perimeter should be 50 centimeters. This is a rectangle. Then perimeter means these people, the outer length, no, total length, right? So then I can choose this way, this length, like 20 centimeters, here 20, and this is 5, then 25, 25, 50, perimeter is 50. Right. Another one more we can select like these people. It is like this. 10, 10, 15, 15, like this. Here also, the total perimeter is people 50. And you can see this way, we can draw infinitely many rectangles so that the perimeter becomes 50. Right now, the perimeter is the same, people, of all the rectangles, right? Some more rectangles we can draw so as to have the perimeter 50. Right. But you can see, people, when we calculate here the area of this rectangle, this is 100 square centimeters. This is 150 square centimeters. Okay. Like that, though the perimeter is the same, the area, people, varies. Then when we find this way infinitely many rectangles, each has an area. Then when we take this way the areas 100, 150 and so on, among these area figures, there is a maximum, greatest one. If we select that corresponding rectangle and see that rectangle is, people, a square. That's what we have to prove. Okay. We can draw infinitely many rectangles so that the perimeter is 50. We separately find the area of each rectangle. Among all these areas, people, there is a maximum area. If you select that maximum area and the corresponding rectangle, you can see that corresponding rectangle is a square. That means its length and breadth being equal. Right? That's what we have to prove. Okay, people. Right. Now let's see how to prove this. Here you are given perimeter. You are given perimeter. Then like this, without taking 50, I'll take this perimeter as, people, L. perimeter of the rectangle I'm going to take as L. And I'm going to take this breadth as y, length as x of this rectangle. Let the given perimeter be simple L. Perimeter is simple L, people. Right. This L is a constant. L is a constant. Why? It is a given value, no? We can't change that given value. It's a fixed value. Always we have to take that same L in forming that rectangle. That's why we say L is a constant. Then if I write an expression for this L, the total perimeter going to be, people, this is 6, right? This is y. Total perimeter, here the perimeter going to be 2x plus 2y. 2x plus 2y equals L. This is first equation we can write. Okay. Secondly, if I take the area of this rectangle as capital A, area A we can write as xy product. Number 2. People, now we need to find when this A, you can see this area A of this rectangle depending on x and y both. X is the length, y is the breadth of the rectangle. Once you change x, due by this equation, y will change. Then once you change x, xy, the y also changes, this xy change. Then capital A change. Right. Now we have to find out when we change like this, A will be coming to a maximum value. That occasion, what are the values of this x and y? And really, we have to prove x and y become equal, then only this will be a square. Right, so people, I'm going to do the question after this like this. By subjecting y by this number 1, in terms of x, we get an answer for y, that I am going to substitute here. Like this, by number 1, we can subject this y. Bring this to right hand side, L minus 2x divided by 2 is the y, this. Then by 2 we can obtain, by 2 we can obtain, people, A equals x times y, L minus 2x by 2. Right now? Now I bring this L inside, this 2 out. Then half, this is Lx minus 2x squared. You can very clearly notice, people, in this case, A depends on x. A is a function of x. That means if we take this A as our y-axis, this is the area now. This as our x-axis. You can see this is quadratic graph. Its x squared coefficient is negative. Therefore, in this case, the quadratic graph should be a maximum 1 because x squared coefficient is negative. You can see there's a maximum value for the graph. That says, people, at a particular x value, the A area will be maximum. Now we need to find out that x value which maximizes this A. Okay. Then by drawing this graph, of course, we can find that. But we'll use the knowledge of the differentiation to get this. Now, you know, people, when A is a function of x, at the maximum point or minimum point, they are called as the stationary points. No? At the stationary points, you know, the first derivative will be 0. Then we first differentiate this A with respect to x. Then we can find dA by dx. Half. L is a constant. Derivative of x with respect to x is 1. Here we get people 2 is a constant. X square derivative is 2x. That 2 and is to make 4x. Right. Now you can say when A is maximum or minimum, dA by dx equals 0. Then you can equate this to 0. And by this equation, you can find x. Okay. Then this L minus 4x equals 0. X equals L by 4. Right, people? That means when this length is equal to L by 4, this A area is either maximum or minimum. That only we know. But people, we don't know exactly what is this A. What will be this A when x equals L by 4, whether it is maximum or minimum. In order to verify that, people, now we can go to the second derivative test or first derivative test. We said last week, people, when something is maximum, the second derivative becomes negative. I'm going to find the second derivative of this. It is d2a upon dx2. Keep this half as the same. L, we said, people, a constant. Then the derivative is 0. Minus 4 times derivative of x with respect to x is, people, 1. Then we get minus 2 here. The second derivative. The second derivative, its right hand side has no x. It says for any value of x, the second derivative is negative. Then even at this L by 4 of x, the second derivative is, people, negative. So therefore we can say d2a upon dx2 at x equals L by 4 negative. Second derivative negative means, people, last week we learned that variable comes to what maximum. What is variable in this case? A. The left hand side variable is come to the maximum. So therefore area A becomes maximum when x equals L by 4. Then you can say therefore A is maximum. A is maximum when x equals L by 4. Then in order to maximize the area of this rectangle, the length of the rectangle should be taken as L by 4. Now let's find when x, the length of the rectangle, is L by 4, what is the breadth y? Put in that x value here, we can find y. Yeah, so then once you find this y will be, I take this 2 like this as half L minus 2 times x, L by 4. Okay, then what do you get there? Y. Here, this and this you can cancel down. L minus L by 2, people, L by 2. Within bracket we have L by 2 multiplied by half means, people, L by 4. Y also L by 4. So what can you say? The value of x and y being equal. Therefore, x equals y. In the rectangle, x and y being equal. This and this being equal. The adjacent sides of a rectangle being equal mean what? the rectangle, people, a square. Understand? Then for a given perimeter, if you draw rectangles, when the area of the rectangle is maximum, the rectangle will be a square, right? And therefore, the rectangle is a square. Hence, it is a square. Hence, it is a square. That's how people we take the answer. Right now, yeah. Right, take it first. Right, people. We'll take the next one, number 90. Question number 90 is the second. Second question is number 90. Number 90. Start, people, number 90. Right, finish this. Yeah, there you are given people like this. Prove that among all the triangles of given hypotenuse. Prove that among all the triangles of given hypotenuse, always the hypotenuse belongs to right angle triangle, people. Right. So then this question regarding a right angle triangle. Prove that among all the triangles of given hypotenuse, the isosceles triangle has the maximum area. That means we draw right angled triangles subject to a same hypotenuse, taking the same hypotenuse, length of the hypotenuse being always the same. Right? First of all, tell me, before going to this, now suppose I'm going to draw right angle triangles with the hypotenuse is 10 centimeters. With the hypotenuse is 10 centimeters. With the hypotenuse is 10 centimeters. Can somebody tell me in how many different ways this triangle of length 10 centimeters of the hypotenuse we can draw? In how many different ways, or how many different triangles, right angle triangles, we can draw so as to have the length of the hypotenuse as 10 centimeters? How many triangles we can draw with the hypotenuse is 10? Just tell me. Really, we can draw infinitely many right angle triangles with the hypotenuse is 10 centimeters. I can, of course, very easily illustrate this one. Suppose the hypotenuse is 10 centimeters. Then I draw first a circle with radius 10 centimeters. Like this. Center is so. Radius is 10. This x-axis, this y-axis, suppose. Then I select a point on the circle as P. I drop a perpendicular from this P on this x-axis like this. 90. Then I join this O and P. Then you can see the triangle formed. It's a right angle triangle. The hypotenuse is 10 radius, no? Another point you can select here. I drop another triangle. Hypotenuse is 10. Another point you can select on the circumference of the circle like this. like that, people. There are many points on this arc. For each point, there's a triangle like that. Infinitely many triangles we can construct with hypotenuse 16. Okay. Now, people, even though this way we have infinitely many triangles with the same hypotenuse, when you find the area of each separately, people, the area will vary from triangle to triangle. You can see that also from this. So there are infinitely many right angle triangles with hypotenuse 10 centimeters. And now we calculate area for each triangle. And among these area figures, people, there will be a highest one. If I select that highest figure and the corresponding triangle will be, people, isosceles right angle triangle. Isosceles means the two sides become equal. That's what we have to prove. Right now, that's the question. Right, so then remember, there are infinitely many triangles. Now, out of them, when you find the maximum area, we have to prove that triangle is an isosceles right angle triangle. Okay. Now we'll come to the question. Okay. I'm going to take this shape. The right angle triangle, I draw like this, and I take its hypotenuse as L. Right? Then given hypotenuse, no, we have to draw the triangle with the given hypotenuse. We are given a particular length for this hypotenuse that I have taken as L. Now we can't change that L, because if we change, then the given one, of course, the one we are given is the is not used, no, people. So we have to use the given thing. Therefore, we are not allowed to change that given hypotenuse. So therefore, L is a constant. L is a constant. And I'm going to take this angle as theta. Hypotenuse is L. L is a constant. Then using this L, I can write, people, this adjacent side of the triangle. Towards the angle, you know the length is L cos theta. Opposite side, people, L sin theta. If I take the area as capital A, you know area of a triangle is half base into perpendicular height. Here, A half base is this L cos theta, height is this L sin theta. Then we can write L and L squared by 2 sin theta cos theta. I multiply this again by 2 and divide by 2. Then this 2 sin theta cos theta you can write as sin 2 theta. This 2 and this 2 make 4, then L squared by 4. Then you can write A equals L squared by 4 sin 2 theta. Like this, we can write. A is the area of the right angle triangle, people, in this case. Now you can see this A area depending on what, people, theta. That means A is a area is a function of theta. That means we can change this area A by changing the angle theta this. Now we should know what is the best angle for theta to get the maximum value for this area A of the triangle. That's what we need to find. Then, you know, after this, what we need to do. People, you know, since A is a function of this theta, we can differentiate this A with respect to theta, because at the maximum value of A or minimum value of A, you know, the first derivative of A with respect to theta becomes 0. Okay, people. So after this, people, we have the question coming under differentiation, right? Then differentiating this, what do we get? dA by d theta. We can write L squared by 4 is a constant, no? Sin 2 theta we can differentiate. We get cos 2 theta multiplied by 2 theta derivative is equal to this and this you can cancel down. We get dA by d theta as L squared by 2 cos 2 theta. Right, people? Now, you know, at the maximum value of or minimum value of A, when A is maximum or minimum, you know, dA by d theta equals 0. Right? Now I can put for this dA by d theta this. Then this is not 0. Therefore, for this product to be 0, cos 2 theta should be equal to 0, people. Cos 2 theta should be equal to 0. This implies us cos 2 theta should be equal to 0. You know, people, cos angle 0 means cos angle 0. Cos angle 0. For the angle 90 only, cos becomes 0. Cos angle 0 means definitely that angle should be 90. So therefore, cos 2 theta 0 mean, people, definitely this 2 theta should be 90. That means pi by 2. Subject in theta, we get theta pi by 4. Okay. Now, people, the summary is when theta is pi by 4, this dA by d theta equals 0. That means the A area is either maximum or minimum, but we don't know which one, maximum or minimum. Then to verify that, we go for the first derivative test or second derivative test. You know, first derivative test, before that value, if the gradient negative, after that value, gradient positive, the curve is like this, then it is a maximum. Okay. But in this case, I'm supposed to use the second derivative test. That means I am going to differentiate this again. d2 A over d theta 2 equals L squared by 2 derivative of cos 2 theta. It is what? Minus sin 2 theta into 2. This and this you can cancel down. d2A upon d theta 2 equal, people, minus L squared sin 2 theta. Now we need to find the sign of the second derivative at this value of theta. Yeah. So then to find that, we can write, people, it like this. Theta pi by 4, it is minus L squared sine. When I put here pi by 4, people, 45 into 2 is 90, sine 90. Sine 90, you know, people, it's 1. Then you can see here d2A upon d theta 2 at theta pi by 4. You can see, people, here L squared, since this is a perfect square, this L squared is positive. Here we have minus sign. Then completely this right hand side is negative. Like this. Then at theta equals pi by 4, second derivative is negative. Second derivative negative mean, people, A is maximum. So therefore, A is maximum when theta is pi by 4. When theta is pi by 4. A is the area of this triangle. Then the area of the triangle is maximum when this theta is pi by 4. People, you know, when theta is pi by 4 here, since here we have 90, this is also pi by 4. These two angles, this and this, are equal now. Then this triangle becomes isosceles triangle. So therefore, we can write the answer. then the triangle is an isosceles triangle. Isosceles triangle. Understand it? This is how we prove that part. Right now? Any question here? Yeah? No question, people. Very good, no? Huh? Very talented guys available in our class, no? And then copy down this. Right? Understand and take down this. Right, paper? Take after this. Question number 94. Question of 94, it says something like this. An open box with a square base is to be made out of given quantity of sheet of area k squared, right? Show that the maximum volume of the box is this. Very practical question, people. A box is to be formed using a given area of a metal sheet, and some conditions must be satisfied in forming this. What are the conditions? First one is the square is the base should be the square. Base of the box should be a square, and the given whole area k squared must be used. There should not be what area of the given sheet remaining after forming the box, and no more area can be obtained as extra area to form what the box. And meantime, the so formed box with that total area of the sheet k squared should have maximum volume. They are the conditions, people. Very practical question. Now, for example, suppose like this, we have a particular given area. Suppose using this area only, we are going to form that box. People, this whole area must be used, and no more area we can use in forming the box, and no area should remain after forming the box. The whole area must be used. See the conditions? And the base of the box should be a square. Meantime, the box so formed should contain greatest possible volume. Very practical one, people. Very practical question. You know, when we form that way an open box, people, if I draw that box like this, you see, is that box. This base should be a square. Right? People know top side open. There are 5 sides for this base, and around that another 4 more sides. Right? Okay, now people, suppose the practical issues when we try to do this without a proper calculation. Okay, now we determine according to our willingness a particular portion for the bottom a square we take like this. Particular portion we take from this as our base. It's a square now. We cut off a square from this as our base, because the box should contain square at the base now. Right. Then from the remaining area of this metal sheet, we are going to cover the 4 sides. Sometimes people, when you cover like that, okay, the area will be not enough. Some extra area we have to take. No allowed for that. Sometimes this area will be more than enough. Particular area may be remaining finally. Also not allowed. Sometimes the area will be okay when we cover the four sides. But there's an issue. There's the issue what? Then we form the box subject to these all conditions, satisfying all conditions. Though that formed box is not the box which can, of course, have maximum volume, we can form by changing the base and the height in the different figures, the same box satisfying the same conditions to have what? More volume in it. See here, the practical issue we get. Right, people? So therefore, if you need to form this kind of box with these resources, people, without having a proper calculation, actually, nobody can determine, according to their willingness, the dimensions of the box. Dimensions means length, breadth, and height. Okay. Practically, if we, of course, get formed this box by a person, those persons, people, they don't know differentiation. As just now we discussed, they take their, according to their willingness, a box, a base, and from the remaining, once they try to cover the four sides, people, sometimes the area not enough, or sometimes some area will remain. Though they completely do that one, people, the volume containing in the box is not the maximum possible one. Using the resources we can form. Furthermore, by changing the dimensions, length, breadth, and height, people, we can form, using the same area, a box with more volume. So in this case, people, when we use the differentiation knowledge very easily, we can give the solution for this. So therefore, this application of derivative is very useful and practical lesson, people. Right. So then I'm going to take here the base is square, no? Then I take the length is 6 and breadth also x, and height I'm going to take as y. Right. Then first we can write area of the total area of the box. Right. The base, length into breadth, x squared. One side x, y. This is xy. Similarly, this part xy. Similarly, this part xy. Similarly, this part xy. Then there are four sides with area xy. Then 4xy. Then total area is this of the box. That total area we take from what the provided area, no, people. Provided area is k squared. So therefore, definitely this area should be equal to k squared, because we must definitely use that given k squared area. I said no. There should not be any area remaining end of the form in this box. So therefore, this is k squared. Number one. Secondly, I'm going to write, people, the volume of the box. V. Volume of this box is, people, base area multiplied by the height, x squared y. Number two. Right, people? Now you can very clearly understand this volume V of the box depends on x and y. X and y. Area A is a function of both x and y. Sorry, not area, volume V. Volume V is a function of both x and y. There are two variables on the right hand side. People, when we get this say two variables, according to our present knowledge of differentiation, we can't differentiate that. When there are two variables on the right hand side of a variable, people, using the usual derivatives, we know the methods, we can't differentiate that. For such function to differentiate people, we learn another kind of differentiation called as partial derivatives. That partial derivative part is not available in our syllabus. But people, when you learn pure mathematics or engineering in the university, you will learn about this partial derivatives. That partial derivatives, of course, for example, if I consider like this, y is a function of both x and z, then we can differentiate this y having now right hand side two variables x and z. Y can be differentiated, people, with respect to x. The notation this time we use is not d, there we use dabba y upon dabba x. This is a new notation, dabba y upon dabba x. That is called as a partial derivatives. Partial derivatives. So therefore, when you find in a differentiation question, usually this kind of this type of situation come in when we work out a question. But the given variable which is to be maximized or minimized coming in terms of two variables. And meantime, in the same question, we get this kind of another equation. This is the people constant. This equation is known as the constraint equation. Constraint equation means subject to that, according to that equation only, the two variable what vary. That is called as a constraint equation. This is the objective equation. Objective means our object is to maximize this, we know. This is called as objective equation. This is the constraint equation. Using this constraint equation, people, one variable in the objective equation we have a subject. Once you subject y from this, that will be coming in terms of x. And if I put that way here, then this volume v will be a function only in x. Now, people, we can differentiate that volume v with respect to x because its right hand side we have only one variable. That's the usual method, people. Okay. Then start this growth diagram. And now we can write like this. Y, we can subject y number 1. We can subject this y. How? Take this x square to right hand side. And divide by 4x. Now this y, people, we substitute y in number 2 for the place of y. Now by number 1, oh no, not 1, number 2. V equals x squared times y. Y is people k squared minus x squared divided by 4x. One x we can cancel down with this 6. Take this 4 out and bring this x in 1 upon 4. When you bring this x in, we get k squared x minus x, and this x squared is x cubed coming. Then you can see the volume v is a function of x. Now I think you can do the rest. You can do the rest. Since v is a function of x, you can differentiate this with respect to what x and take the dv by dx, equate that to 0, find the x value, and using second derivative or first derivative test, you can show at that x value the volume v becomes maximum. Then you can come to the end of the question. Okay, right. Do that part, people. I'll give you a few minutes. By multiplying length and breadth only, we get k squared. Therefore, k is a positive because k is the length there. Right. Now we can differentiate this with respect to x. dv by dx. 1 upon 4 you have to keep like there. Here, k squared x, when you differentiate, k squared is a constant, keep it as the same derivative of x with respect to x is equal to 1 minus here 3x squared. Then we get like this. Then, people, when this v is either maximum or minimum, this dv by dx is 0. When v is maximum or minimum. dv by dx equals 0. That means 1 upon 4 q squared minus 3x squared equals 0. Now, this into this equals 0 mean this bracket should be 0 people. Take this right hand side and subject x squared. X squared will be q squared by 3. When subject x taken root k upon root 3. We don't put to right hand side plus or minus. Why? The reason is, people, this x is the length of the base of the box. Length is always positive. Though you put that plus or minus, again we have to project minus sign and we have to select plus. So I straight away took this. Now k is this, x is this. That means at this value of x, the volume v of the box is either maximum or minimum. Now we have to exactly verify. At this value of x k upon root 3, the volume v is maximum. For this, I am going to take the second derivative. Differentiate this second time. d2 b upon dx2. 1 upon 4 k squared is a constant 0. Here 3 is a constant, x squared derivative is 2x. Then this 2 comes here, minus 6x coming. Then cancel in this and this by 2, we get 3 here and 2 here. Then d2v upon dx2, we get minus 3x by 2. Now I'm going to find the sign of this second derivative at x equals k upon root 3. Once I put that, minus 3 divided by 2, this x is the value k upon root 3. You know this k is a positive value, people. K is a positive value. Then since this minus sign, this right hand side becomes negative. Therefore, you can say d2v upon dx2 at x equals k upon root 3 negative. When the second derivative is negative, people, that becomes maximum. Therefore, v is maximum. Therefore, v is maximum at x equals k over root 3. Okay? Yeah. That means, people, in order to maximize the volume, the length of the base should be chosen as k upon root 3. Then we have to decide why. Why can easily be decided, people, that x value we found here, we can put here and simplifying, we can take y. In this way, when you select this X and Y people, that given area will be sufficient for the purpose. That means no extra area needed and no area will remain as unused one. All the area will have been used. Meantime, the base is a square. Meantime, with the available resources, the formed box is the one containing greatest volume. Okay. Now our answer, we need to find the answer, the greatest volume, the maximum volume. Then we have to find that too. How to find that, people? That found X value, we have to substitute here and here. Then we get V corresponding to that X value. That volume will be the maximum volume of the box. Why? We proved that here. Okay, then you can write, therefore, V max, maximum volume, V max. Maximum volume, V max. One upon 4 K squared times X, K over root 3 minus X cube, K cube upon root 3 cube means 3 root 3. This K cube I can take out. We will take 3 root 3 as a common denominator. Then here this place now we have 1. When you take the 3 root 3 as a common denominator, here we get 3. Here we have minus 1. Then 3 minus 1 is 2. 2 and this 4 you can cancel down. Here we get 2. 2 into 3 is 6 root 3. K cube upon 6 root 3. Is the maximum volume of the box. Now, people, practically, if you need to form this kind of box, people, we have to first calculate using your differentiation knowledge the length and width and the height. And now you have to go for the person to get it made, people, giving these parameters. Otherwise, you won't get what? The box with the available area you can form to have maximum volume, right? Very practical. But actually, to get this done, people, nobody available in our society, because the people, they do these things, people, they don't have much education, no more education. Then they don't know anything about this differentiation. Then we won't expect this kind of service by our people. The people, they know this one, they don't do such jobs. So therefore, that is why our countries usually not people developed. Right. Okay. Next one. Take question number 101. Question number 101 as the next question in your tutorial. 101. Read this question. Question number 101. People, here you are given prove that the volume of a largest cone that can be inscribed in a sphere is 8 upon 27 of the volume of the sphere. Prove that the volume of the largest cone that can be inscribed in a sphere is 8 upon 27 of the volume of the sphere. What is this, people? Now, suppose you are given a hollow sphere like this. A hollow sphere like this. In this hollow sphere, people, we are going to keep a right circular cone. You know, cone means this shape, no? Circle means the base is radius. Right means the center and the vertex of the cone when we join. This is called as the axis. This axis is perpendicular to the base. This is called as the right circular cone. Suppose this kind of cone is formed with a particular stretchable material. This kind of, suppose this shape, a balloon, the material with which the balloon formed, right? We form like this so that we can inflate this. We can pump air into this. Now, once we pump the air, the volume is increasing, keeping the shape as the right circular cone. This cone is now formed with a particular elastic material. And once we inflate, when we pump air into that, the volume is increasing, keeping the shape of a right circular cone. Now, once we keep like this, people, inside this cone, once we inflate, once we pump air into that, you can very clearly see this volume of the cone gradually increasing. One occasion, the volume value of the cone, then no longer the volume of the cone can be increased. No space inside the hollow sphere for furthermore to increase the volume of the cone. That moment we get one occasion. That occasion, people, if we measure the volume of the cone, it is the maximum volume of the cone. And that volume of the cone we need to prove is 8/27 of the volume of the sphere. The sphere is a fixed one. Its radius is fixed. That's the question. Right. People, then how to work out this question? Right, we have to understand this way. Now, while we inflate, the volume of the cone is increasing. Once the volume of the cone is increasing, the cone, it uses the inside space of the sphere symmetrically. What do you mean by symmetrically? The cone occupies the space inside the sphere equally everywhere. Now you can very clearly understand when we consider a classroom this way, people, a classroom. Suppose some benches we have to, or desk we have to prepare in the classroom with the shape this. People, you can very clearly understand. If we, of course, prepare the benches or the desk in this way, people, you can see we can't place more desk in this. Because the preparation, the arrangement of the desks are symmetrical, not symmetrical. Rather than this way, people, if we arrange this all benches or the desks in this way, people, you can very easily see more desks we can arrange in the classroom. See here. So here, unnecessarily, some spaces we can't use because of the arrangement, irregular arrangement of the desks. That says, when we utilize something in this way, whenever we utilize it, it's of course all resources, people. That thing, when we arrange this way, symmetrically, the disk should be arranged. Symmetrically means here above this line, left and right being people equivalent. Like that, while we increase the volume of this cone by inflating it, okay, as the volume of the cone increases, the cone occupies the inside space of the sphere symmetrically. Symmetrically, in this case, mean people, the axis of the cone passes through the center of the sphere when its volume comes to the maximum. We have drawn that diagram, people, and thereafter we can work out this question. Okay, then we write like this. Write down, when the volume of the cone becomes maximum, the cone lies inside the sphere. The cone lies inside the sphere. The cone lies inside the sphere symmetrically. Symmetrically. That is, the axis of the cone passes through the center of the sphere. Passes through the center of the sphere. Passes through the center of the sphere. Right, like this, people. This is the center of the sphere O. All right, I am going to take the radius of the sphere as R. It is a constant, huh? It's a constant. Right? First draw the diagram. When you join this O and this vertex, this and this is also radius R. Radius R. This is the right circular cone, therefore the axis is perpendicular to the base. Axis is perpendicular to the base. Now I'll take this height as x. It is a variable now. Okay. I will write another one sentence. Let the radius of the sphere be simple r. Right. Now people, the radius of the cone is this. That one you can very easily find. How, people? Using the Pythagorean theorem to this triangle. Here 90, no? Then hypotenuse squared minus this side squared x squared root is this r squared minus x squared root. Now you can write the volume of the cone V. What is the formula for the volume of a cone, people? 1/3 base area into height. 1/3 pi r squared h. H is the height of the cone. It is in this case r plus x. Pi r squared means square of this. The root will eliminate. 1/3 pi r squared h means r plus x. Then you can see here, people, the volume of the cone V is a function of x. Right? Then by changing this x means this height, we can change the volume of the cone inside the sphere. Now we are going to find out the best value for x, which maximizes the volume of the cone. Now the rest part you can do, people. What we do? We differentiate this V with respect to x and we find dV by dx. And when this V is maximum or minimum, dV by dx, people, becomes 0. Then equate that dV by dx to 0. And find x. Then using either first derivative test or second derivative test, at that value of x, show V is maximum. Thereafter, find the maximum V. When you find that maximum volume V of the cone, people, you will see that volume is 8/27 of the volume of the sphere. Right? Right. I'll give 5 minutes, people. Right. Yeah. Now we can differentiate this dV by dx. This pi by 3 we keep as the same. Then we follow this as u into v form. Keep this u as the same. Derivative of v, r is a constant, 0. Derivative of x with respect to x is 1, people. Plus, keep this r plus x v as the same. Mark that by the derivative of this u. R squared is a constant, 0, minus derivative of x squared is, people, 2x. Then we can furthermore simplify this dV by dx. Pi by 3 r squared minus x squared here minus 2rx minus 2x squared. This we did. We get dV by dx, pi by 3 minus x squared and minus 2x squared is minus 3 x squared minus 2rx plus r squared. I'll take this, people, minus sign out. Then we get minus pi by 3 3x squared plus 2rx minus r squared. You can obviously see here, this is the quadratic equation in x. Quadratic expression there in x. You can factorize that. Can find two factors here. Three x and x here. You see. See here, what do you get? 3x and x, 3x squared. 3x into r is 3xr. Here minus xr, 2rx. R and r with minus sign minus r squared. We get like this. Even this x is a length, no? That is this length, no? This length cannot be negative. Length is always positive, no? Then obviously, this factor is positive. Okay, then I can further take this 3 out. dv by dx, once I take this 3 out from this bracket, this 3 comes out, that will cancel with this 3. Then we have minus 5. Once you take this 3 out, this r should be divided by 3, like this. Like this. Now for maximum or minimum volume. For maximum or minimum, you can write, people, dv by dx equals 0. Then I can write minus pi times x minus r by 3, x plus r is equal to 0. So then we can equate this to 0, x minus r by 3 is 0, or x plus r is 0. This gives us x is minus r. This gives us x equals r by 3. But this is impossible, people. Why? X equals minus r is impossible. The reason is x is a length, r also a length. Then x is negative, mean length will be negative. Therefore, x minus r is impossible. We reject that. Then x equals r by 3. Now we have to prove at this x value, r by 3, the volume V is maximum. This time to verify that, people, I'm going to use first derivative test. So far we used in every question second derivative test. No, I'm going to use now first derivative test. When we need to show something is maximum, people, before that value we have to prove the gradient is negative. After that value we have to prove gradient is, so before that value gradient is positive, after that value gradient is negative. Okay, then we have to write this way, dv by dx x less than r by 3, x less than r by 3. Yeah, this is the dv by dx expression. We have to find the sign of this dv by dx. When this x in it, this and this less than r by 3. There, people, this x plus r is always positive. Okay. Then no need to put that x value where here, because for any value of x, this is positive. Then the sign of this dv by dx depend on these, people. Yeah. Then when I put a value for x, this less than r by 3. Less than r by 3 means this place will take a value which is less than this r by 3. Then this is smaller, This is greater. The difference is negative. That negative and this negative make positive, people. Then we can say dv by dx x less than r by 3 is positive. Similarly, we can write, people, dv by dx x greater than r by 3. This is positive. This is positive. With this, we get minus. Okay. Then we can very clearly see here, when we consider the graphical interpretation here, this is the V volume axis. This is the X, what? This variable. By changing this X only of the volume of the cone, then we notice that X R by 3, the dV by dx 0. Then at X R by 3, dV by dx 0 means the gradient is 0, then the line tangent is parallel to x-axis. Before r by 3, look at this. dV by dx is positive. That means this way. After r by 3, dV by dx is negative. Then this way we get something. Therefore, obviously, you can see at x equals r by 3, the volume V is maximum. This is how we use the first derivative test. Okay, therefore, you can write at x equals r by 3, the volume V of the cone is maximum. Then you can write therefore, volume V of the cone is maximum when x equals r by 3. X equals r by 3. Okay, right. Now we need to find the maximum volume. Right. This is a volume formula for the cone. In it, this x, just now we found r by 3. Put that here and keep simplifying this. That volume only, people, we have to prove. It is 8 upon 27 of volume of the sphere. Right. Then you can write. Therefore, V max pi by 3, right, r squared minus x squared. X is r by 3. Perfect squared. R plus 6. Now people simplify this. R squared, here we get r squared by 9. Here we get 4r by 3. Here take common difference 9. 9r squared minus r squared is 8r squared. Here 4r by 3. Then I take it like this. This 4 r squared and r cube and this 3. Then we get 4 by 3 is 5 r squared and r cube. Now that this 8, 10, 3 into 9, 27 we have. I write it like this. 8 upon 27. This is the volume of the maximum volume of the cone. This is the maximum volume of the cone. This is the maximum volume of the cone. People, when you very carefully look at that, you can see. What is this? 4 by 3 pi r cube. 4 by 3 pi r cube. It is the volume of the sphere. So therefore, we can write maximum volume of the cone 8 upon 27 multiplied by 4 pi r cube by 3 mean of 4 pi r cube by 3 means volume of the sphere. Correct now, people? Then maximum volume of the cone is 8 upon 27 of volume of the sphere. That's how people we take that answer. Right now? Yeah. But as the next question, take 102. Question number 102. Question number 102 is the next question. Right, people, think this question and try to get this answer. I'll give you 5 minutes and start. Right, people, this time, what is the question? A cylindrical can is to be made to hold 1 liter of oil. A cylindrical can is to be hold 1 liter of oil. Cylindrical can. You know the meaning of can, people. So you have actually seen this kind of can. The top and the bottom both closed, people, and there's a hole here to fill that liquid, and there's a handle like this. The round surface is the cylinder, bottom and top both closed. Yeah. So now we have to form this can to hold 1 liter of oil. That means the capacity of the can should be 1 liter. 1 liter means, people, 1000 cubic centimeters. 1 liter, 1000 cubic centimeters. Right. Find the dimensions which will minimize the cost of the metal to make the can. Find the dimensions. People, dimensions means what? The base radius and the height. Dimension of a particular object mean, in order to explain about that, what are the things we have to use? They are called as the dimensions. Using this height only, people, we can't completely explain about this can. In addition to height, the base radius also we need, because by changing the base radius also, the volume of the or the capacity of the can will change. So therefore, in any object, people, in order to explain it completely, what are the things we have to use? They are called as the dimension. When we consider, people, a box, what are the dimensions? Length, breadth, and height. 3 dimensions are there. This time, dimensions mean, people, the base radius we have determined, and this height h we have determined. Right. For a while, I am forgetting this and this hole. The both top and the bottom should be closed. Even in this case, this can is expected to make by using metal sheet. By using metal sheet. So something like this, a metal sheet we use, and by folding this way, people, by curving like this, we can take the the curved part of the can. And now the top and the bottom we have to close by distance. Okay. Now, when we make this way, the can, people, we have to, of course, buy this metal sheet. When we buy the metal sheet, people, when the area of the metal sheet we need increases, in buying them, people, we have to spend more. We have to spend more. Then we have to make sure to buy minimum possible area of this metal sheet, which we need to make this can. So therefore, minimizing the cost of producing this can mean, people, we have to minimize the expenditure we have to bear in buying this metal sheet. To minimize in buying this metal sheet the expenditure, people, we have to minimize this area. So therefore, people, minimizing the cost of producing this can mean we have to minimize the area of the metal sheet which we use to form this can. So for our object is to minimize the area of the overall can so as to hold 1000 cubic centimeters of volume in it. So therefore, our object is to minimize the area. If area is minimum, the cost is minimum. Okay, now minimizing the area, we have to form a cylindrical can to hold 1 liter volume in it. Okay, right. So therefore, our object is to minimize the surface area of the can. Then only the cost will be minimum, right? So then we'll work out this. I'll take this base radius as R and height of the can as H. First, we'll write, people, one expression for volume. Volume of a cylinder, base area pi r squared into height H, the volume, right? This volume should be, people, 1 liter. That means 1000 cubic centimeters. Okay. Volume V is pi r squared H. Volume of a cylinder, base area into height H. That volume V should be equal to 1000 cubic centimeters. 1 liter means 1000 cubic centimeters. So therefore, the first equation we get, people, here, pi r squared H is 1000. See, number 1. Then secondly, you can write, people, the area of the overall cylindrical can. 3 surfaces, 2 flat surfaces like this and curved one like this. Right. So then if I write the area as A, the 2 flat surfaces, pi r squared and pi r squared, 2 times pi r squared plus. And people, when we consider this way, this sheet, it's a rectangle at the moment, right? When you, of course, fold like this, this is cylinder now. The area of the cylindrical part mean, people, this whole circumference into height. The circumference is going to be, people, the length. Then 2 pi r is the circumference. Okay. Into H is the area of the curved part. 2 pi r H. Now this A we have to minimize. Then only we need to buy minimum area of the metal sheet. Then only the expenditure will be minimum. Then we have to find out this R and H so as to minimize this A. Okay, then you know this A area is a function of both R and H. Having two variables on the right hand side, we know we can't differentiate. Then what we do is, by this number 1, we subject H and we put that H here. Then this right hand side of this A we get in terms of people what? R. Okay, this is number 2. By 1 we can write H equals 1000 divided by pi R squared. Put that in number 2. Now by 2, A equals 2 pi R squared plus 2 pi R times H. This pi and this denominator pi we can R and R squared R we can cancel down. We get A equals 2 pi R squared plus 2000 divided by R. Then you can see A is a function of R, right? Differentiate this A with respect to R. dA by dr. 2 pi is a constant. This R squared, this 2 coming before this. We get 4 pi. R squared derivatives people, 2R1, then 4 pi R coming. Right? And when you differentiate this 2000 divided by R people, you have to first bring this R to the power R to this numerator. But bring this R to this numerator. That will be R to the power minus 1. Power minus 1, when you differentiate, what do you get? Minus 1 comes before R, minus 1, minus 1, minus 2 coming. Then that minus 1 will bring this term completely minus. Minus 2000 into R to the power minus 2, no? New power of R. Once I bring this R to the power minus 2 to denominator people, that will be R squared. This is what we get. Okay. Then, when this A is either maximum or minimum people, we know this dA by dr should be equal to 0. When A is maximum or minimum, dA by dr is equal to 0. We get 4 pi R minus 2000 divided by R squared equals 0. We can cancel down this by 4. Then here we get 5 times R, bring this right hand side, 500 divided by R squared. We can use a cross multiplication like this. Then R cube equals 500 divided by 5. Then R can be subject to taking the cube root of this. People must do work, questions as homework, right? You can find R. Take the cube root of this. 1/3 power is R. Right. Now, at this value of R, the area A is either maximum or minimum. Okay, either maximum or minimum. Now we have to verify really it is minimum. What? A minimum at this value of R. For this, what we do is we go to second derivative. Differentiate this again. Differentiate this again. Right. Now when you differentiate this again, what do you get? This one, second derivative we get d2a upon dr2. Here, 4 pi is a constant, derivative of r with respect to r is 1. Then here we get 4 pi. And minus 2000. We can take this r square to numerator. That will be r to the power minus 2. Power minus 2, when we differentiate, what do we get? Minus 2 comes before. R, new power is minus 2 minus 1. Minus 2 minus 1 is new power of r is r to the power minus 3. That r to the power minus 3, when you take to denominator, r to the power plus 3. Then here, this 2000 should be multiplied by minus 2. With this minus sign, minus plus 2 into 2000 is 4000. Plus 4000 divided by r cube comes. Okay. Then you can very clearly see here, we need the second derivative value of a when r is this. R is this means r cube is this. To show a is minimum, people, we have to show the second derivative is, when it's a minimum, second derivative is people positive, no? Yeah, we said that, no? Yeah. So then we can write d2a by dr2 at r equals that 500 divided by pi to the power 1/3. Mean people here 4 pi plus 4000 divided by r to the power 3. When r is this figure, when r is this one, r to the power 3 is going to be this. Then here I have to put r to the power 3, 500 divided by pi. Then here we get people 8. This pi goes to here. Then we get 12 pi as a second derivative value. Obviously, this is positive. Second derivative positive means people that a is minimum at the value of r this. Right? Therefore, you can say, therefore, a is minimum when r equals 500 divided by pi to the power 1/3. When a is minimum, surface area is minimum, people, the cost of production will also be minimum. Then, to minimize the cost of production of the can, the base radius of the can should be chosen at this value. Not only that, the height also we need. Height can then be found, people. H is given by this, no? Its right hand side r be replaced by this. Then we get h. Right? A dimension means the area, the r and h both. Right? Then you can write. Therefore, h. Therefore, h equals 1000 divided by 5 times r squared. 500 divided by pi, 1/3 is r. It's perfect square we have put. Okay. Then when you multiply this power with this 2, people we get power 2/3. Then h comes as 1000 divided by pi times 500 divided by pi to the power 2/3. Right. We can simplify this, people, furthermore. How to simplify this? H equals here pi to the power 2/3. Here pi to the power 1. When you simplify this pi and this pi to the power 2/3, here we get denominator pi to the power 1/3. This 1000 I can write, people, 2 into 500. Here 500 to the power 2/3. Here the numerator power 1. Then how to simplify? This and this, when you simplify, we get 500 to the power 1/3 to the numerator, no? That is simple algebra, right? Arithmetic simplifications. 2 500 to the power 1/3 and 5 to the power 1/3. Then h comes as, people, this way. What? 2 times 500 divided by pi to the power 1/3. In other words, people, this is r, no? That is this r. Then h will be equal to 2 times r. H is equal to 2 times r. So therefore dimensions are this. Therefore dimensions you can write. Therefore dimensions r equals 500 divided by pi to the power 1/3. H equals 2 times of that. They are the dimensions. That's how we write that answer. Okay, some more questions available in that type. Try to do them as homework. Now we come to the next application. Right? Let's first complete this. Next type of application is, people, equations of tangents and normals. Right. Write down next subheading as this way: equations of tangents and normal. Tangent and normal. Equations of tangent and normal. Tangent and perpendicular. Normal means perpendicular. Right, people, now you should understand 2 theories which we discuss in the straight line lesson in the future. And people, those theories already we have discussed in the cooperative forces second part in finding the equation of a straight line. Right. Those idea we need, people, because when we do that kind of questions also in this part, then all types of applications we can finish in this. And next day we can start, people, the next application sketch in the curve sketching part. Now that notice this. Now suppose, people, we have a straight line. That line has the gradient m, and the line passes through a point x0, y0. The equation of this line we can write, people, y minus y coordinate of the point on the line equals gradient times x minus x coordinate of the point. This is the way of writing the equation of that line. So therefore, in order to write equation of a straight line, we should have its gradient and we should have a point on the line. Point x and y coordinates both we should know. If we know that two things, what? Gradient and x and y coordinates of a point on the line, people, using this, we can find the equation of the line. How? Y minus y coordinate of that point equals gradient times x minus x coordinate of that point. That is the first thing. Number two. Okay. Suppose we have a line like this. Suppose it's L1 line. Suppose the gradient is M1. Consider another line which is perpendicular to this L1 with gradient M2. Line is L2, gradient M2. When these two lines L1 and L2 people are perpendicular to each other, we can prove the product of the gradients of this line M1 multiplied by M2 is equal to minus 1, right? M1 multiplied by M2 is equal to minus 1. We prove this one. We are in the straight line lesson. Until then, to work out some questions, we'll use this directly without proof. Okay. Then first write down the knot. Write down the knot. Write down knot. First one. The equation of the line. Note number one, right? The equation of the line with gradient simple m passing through the point P x naught comma y naught, passing through the point P within bracket x naught comma y naught. That's a note number one. People draw that first line and write down under that the equation of the line as y minus y naught equals gradient m times x minus x naught. First knot, draw the line and write that equation y minus y naught equals m gradient times x minus x naught. That's the knot number one. Second, people, knot number two. Knot number two. Write down like this. Let the lines simple L1 comma simple L2, simple L1 comma simple L2 with the gradient simple M1 and simple M2 respectively. Simple M1 and simple M2 respectively are perpendicular to each other. Are perpendicular to each other. Then M1 multiplied by M2, M1 multiplied by M2 equals minus 1, equals minus 1. Right, people draw the second diagram and write down again that M1 M2 product is minus 1. Okay. The result of this people we understand this way also. Now, when I subject this M2 by this, or M2 equals here, bring this M1 to right hand side denominator, minus 1 upon M1. What is this? If you have a line with gradient, suppose m1, then the gradient of the line which is perpendicular to this can be obtained how? Take the reciprocal of this gradient, 1 upon m1 is that, and multiply that by minus sign. That means, for example, we have a straight line like this with the gradient 2/3. Then the gradient of the line which is perpendicular to this, the gradient of this line can be obtained. Take the reciprocal of this. Reciprocal means people interchange numerator and denominator. Okay, and multiply that by minus sign. That is how we find the gradient of the perpendicular line. Okay, yeah. Using this, people, we can answer some questions. This is a well popular theory part in the part A questions in pure people, right? Most of the time when you go through 10 papers, out of that 10, more than 6 papers, a question usually come in by this. Yeah. So we'll see by doing one question to understand this theory, right? I'll write down like this. One example. Write down, find the equation. Find the equation of the tangent and the normal of the tangent and the normal drawn to the curve y equals x cubed plus x squared minus 1. X cubed plus x squared minus 1. At 1, 1 on the curve. At 1, 1 on the curve. At 1, 1 on the curve. Right. Right. Now we can actually draw this curve. Any equation for a curve, people, there's a corresponding graph. Right. In the next application of this differentiation, we learn how to draw the graph of this kind of equation when we are given. People, I am going to assume the shape of the graph in this case of this, not the exact accurate one. I am roughly considering the graph of this equation like this. Its equation is now this. Okay. A point on this graph lies P 1, 1. On this graph, we have a point x coordinate 1, y coordinate 1. At that point, we draw a tangent. Tangent means a line that touches this curve at that point, like this. This is called as a tangent. This is a straight line, no people? This is a straight line. For the straight line, there's an equation. And at the same point P, we draw a line perpendicular to this tangent. We draw another line perpendicular to this tangent at the same point P to this curve. That line only, people, we defined as the normal line. Normal line. Normal means perpendicular line. Normal line is this. So then we need to find out the equation of this and this. Right? Okay. Then to find the equation of a straight line, we can use this. Whenever you use that, people, remember, we should know the gradient of that line as well as a point on the line for x naught and y naught to substitute. As our x naught, y naught people, we can use this 1 and 1. That's okay, because the 1 and 1 point is on this tangent as well as on the normal. Then as our x naught, y naught, we can use that 1 and 1. Now we need this m. M is the gradient. If you can find the gradient of this tangent, since this normal is perpendicular to this tangent, taking the reciprocal and multiply by minus sign, we can take the gradient of this normal. Let's find the gradient of this tangent. People, can you tell me the way of finding the gradient of this tangent? Can you remember we said what? By dy by dx, we get what? Gradient, no? And furthermore, we said what, people? Gradient of a given curve at a given point on the curve, gradient of a given curve at a given point on the curve is equal to the gradient of the tangent drawn to that curve at that point. If we need the gradient of this point of this curve, we have to first construct a tangent at that point of this curve, and we have to measure the gradient of this tangent. It is the gradient of this curve. The gradient of the curve is given by dy by dx. That also we proved. Then, people, to find the gradient of this tangent, we have to differentiate this y with respect to x, and we have to find dy by dx. Dy by dx is gradient. By differentiating this and finding dy by dx, and on its right hand side put in x equals 1, because we need the gradient at 1 point. No, x quality is 1 of the point we need the gradient. Putting that 1 on the right hand side, people, we can find what? Gradient of this tangent. Then m is known. Put in x naught 1 and y naught 1. Using this equation, we can find the equation of the tangent. Then of that gradient taking reciprocal, you can find the gradient of this normal. And again, 1 point is on the normal. No, using this again, you can find the equation of the normal. Right, that's the method, people. Okay, now start. First, draw a rough sketch of the graph. This is not the exact accurate graph, people. I just drew this one to put our information in it. Right, we can write here y equals x cube plus x squared minus 1 dy by dx. We can write, people, here 3x squared plus 2x. Now we need the dy by dx at 1 point, no, but the dy by dx expression contains what, people? Only x. Then we write here this way to give that idea what? We need the dy by dx at 1 point. Put 1 for x on the right hand side. 3 into 1 square plus 2 into 1. This is 5. The gradient of this tangent is, people, 5. Gradient of the tangent is 5. Then you can write equation of the tangent by using this. Therefore, the equation of the tangent. The equation of tangent, people, y minus y naught. Y naught means the y coordinate of the point on the line we know. It's 1. Equals gradient is 5m x minus 1. Then remove the bracket, 5x minus 5, y minus 1. Bring all these terms to this side. Y minus 5x plus 4 equals 0. The equation of the tangent is this. Right, equation of the normal. What do you get there? Y minus 1 gradient, space, we put a bracket here, and x minus 1. What is the gradient of the normal, people? We said the gradient of the normal can be obtained. First, take reciprocal of this. Phi means 5 by 1, no? Reciprocal means 1 upon 5. That should be multiplied by minus sign to get the gradient of the normal, minus 1 upon 5. Then use the cross multiplication by this 5. We get what? 5 times y minus 5. We have minus 1 here, minus 6, minus plus 1. Bring this terms to this side. X plus 5y takes this side minus 1, and with this minus 5 minus 6 equals 0. These are the equations of the tangent and people, but normal. Okay.